Solar power is the most abundant, most renewable resource we have, and it's free. Sunlight is composed of packets of energy called photons. Solar cells convert the energy in sunlight into electrical energy. The process relies on the photoelectric effect, which is when matter emits electrons upon the exposure to electromagnetic radiation, such as photons of light. Solar cells take in energy from the sun and convert it into electrical energy, which we use to power our lights and appliances. Plants also convert energy from sunlight, but they convert it into stored chemical energy in photosynthesis. Plants contain a pigment called chlorophyll, which absorbs the sunlight, whereas in solar cells, the same act is performed by a semiconductor. Silicon is used as a semiconductor in solar panels. Silicon has 4 electrons in its outer shell. This means that it can form 4 chemical bonds with 4 other silicon atoms. This makes a crystal structure. In this state, silicon will not conduct because there are no mobile charge carriers. If you add impurities, you can make it a better conductor. This is called doping. If you add traces of phosphorus, which has 5 valence electrons, it bonds to 4 other silicon atoms, but it will have a spare electron. This electron is available for conduction. This is called an N-type semiconductor. If you add a trace of boron, which has 3 valence electrons, it tries to bond with 4 other silicon atoms, but it can't because it doesn't have enough electrons. It can only bond with 3. This leaves a positive hole, which can move around the structure, allowing conduction. This makes a P-type semiconductor. When you sandwich N-type and P-type semiconductors together, you create a PN junction. Some of the electrons in the N layer see the holes in the P layer and rush down to fill them, making electron-hole pairs. This creates a barrier, stopping more electrons crossing over. The loss of electrons in the N layer leaves behind a positive charge on one side of the junction, and the gain of electrons in the P layer creates a negative charge on the other side. An electric field is created. The PN junction will only allow electrons to move in one direction, from the N layer to the P layer, because of repulsive forces. When a photon hits a solar panel, it can excite more electrons in the N layer. These become free for conduction. If the photon has enough energy, it can excite the electron across the barrier at the PN junction, over to the P side. The electron which has crossed the barrier is separated from its hole. It wants to recombine with it, but it can't. If we connect an external wire between the 2 semiconducting materials, the electrons can flow through the wire and recombine. As they flow back to the P side, the energy can be used to generate electricity.